Excellent. So thanks for joining me this afternoon. I can see through the darkness that many of you are holding the book that you got on our stand. And so this talk is a bit of a summary, a bit of a narrative of that particular chapter and the experience that we learned by building a system that evolves, and that evolves for a long time. So by these long-lived microservices, I obviously don't mean stuff that runs for days, weeks, months. You know, I write software, you write software, we know it crashes. What I mean is things that can survive long-term evolution of the system. And so we'll look at some of the patterns that we've used. We'll take a look at architecture, and then obviously we'll take a look at lines of code. You have the books. I'll show you a link to GitHub repo that contains all the code, so you can build and try for your pleasure. Remember to vote. I was going to edit out the other two smiley faces and leave just the one that you should press, but you know, I can't make you press anything, which is a shame. So let's start with the design and architecture. The thing you have in the books in front of you, for those of you who don't have it, we still have a few copies left, it was a relatively simple system, right? An image goes in at number 1. So people pull out their mobile phones and they take a picture of a document, like a passport or a driving license or stuff like that. Magical processes happen in step 2, and then we deliver the results to, say, a gambling company or a bank that says, yes, this is a genuine thing, or no, this is really a little bit suspicious, and you shouldn't allow the transaction to go through, you shouldn't allow the account to be opened. So you think, oh, how hard can that be, right? This feels neatly stateless, no trouble at all. Well, trouble is obviously with scale. So a lot of the computation happens on the user's phone. That's kind of nice. But then if we have hundreds and thousands of people using their phones to push stuff into our ingestion service, that's where a lot of traffic comes in. These images are big. So you're looking at 2 to 4 megabytes per image that then needs to be processed and analyzed. The processing, well, you know, that's still some work. We can run it in parallel. Suppose we can. Suppose this is like a really easy system, or we could run all these processes in parallel. And then as soon as one of these processes finishes, so there might be one that says, okay, is it tampered with? And then it says, no, not tampered with, and immediately we push the result out to our customer. So even if we survive points 1 and 2 with the load from the users, we could be really, really, really bad to our customers, because their systems might not be ready for, say, 1,000 requests in a very short period of time. I'm not going to say 1 second. So without the details, it's nice and simple. With the details, it gets a little bit more complicated. So let's add complication. We're going to add this summary service, which maintains some state, right? You don't want to send these tiny, tiny messages to everyone saying, we've done, you know, document integrity check. Okay, well, that's kind of nice, but I want to wait until the whole thing is ready. And there might be some magical business logic in this summary service that says, okay, well, you know, a document with these particular features is usually invalid. Anyway, so we have that, and we're going to separate out this push service. We're going to make it a bit more friendly to our customers. So if our customers cannot keep up, remember, this is outside of the scope of our system. Normally, everyone tells you should be back pressure aware. Okay, that's great, and you can have all the back pressure you want inside your system. You've written it. Once the stuff goes outside, you don't have anything. All that you need to do is to react to maybe someone gives you, you know, a 503 over capacity, and then you say, okay, well, I'm going to stop for a bit. But that requires some sort of persistence. You don't want to lose the requests. Alternatively, there is this firehose concept. Anyone tried the Twitter API? Come on, we all built tweet apps, right? So you can do this long-running post, and you get these chunks of HTTP requests that you can consume essentially at your leisure. So we can do that as well with this firehose API. It makes it easier for our clients, because in the first push instance, they have to implement some sort of endpoint that we call, right? We push the stuff to, which is easy to do, right? Not a problem, but it makes our system responsible for checking that it is talking to the right thing, right? So we should say, okay, this is over HTTPS, great. Now, but it's our problem. We should check that we're talking to the right endpoint, and the certificate matches and all that. In the reverse case, with the Firehose service, the clients make a call to us. They can verify what they want. Is it really our system? And they consume the HTTP chunks. So the details. Oh yeah, and this stuff, right? I mean, these connections are great. We can all look at them on these architectural diagrams, say this is kind of cool, right? This ingestion service connects to these processes, but what is it? And how does it actually work? How does it guarantee that the messages will get to one of these processes? How does it guarantee that they won't get lost? So we need to take a look at that. Next thing is, everyone keeps telling us, okay, reactive systems, they want to be resilient. So we need to tolerate failures, you need to treat failures as first-class citizens. Okay, well, what if that database fails? There is some sort of storage. What do we do when it disappears? What do we do when it's not available? So we'll need to dig into that as well a little bit. In the push service, again, we need to see how we can deal with back pressure in a reasonable way. And similar story for the Firehose service. How do we group things? How do we group these recorded requests so we don't overwhelm our clients? And then these stateful services. Oh man, this gets even more complicated. So suppose, again, that's in the book, and I've made up an example here. Let's say we need to receive 3 messages before we can produce an output. That's not too hard, right? You need, document the front of it, the back of it, and the picture of a human. And then you can say, okay, this is all the right thing, and the picture matches. Cool, so you need to receive message 1, message 2, message 3. How do you make sure that your system survives a crash? So I have this summary service running. It's all cool, receiving messages, and consumes the first message. Okay, it moves to some incomplete state, it receives second message, moves to some incomplete state, and crashes. What do we do? How do we recover from it? So, you all know the answer, right? We have some sort of event sourcing, we have some sort of persistence. So the next question is, where is this stuff persisted? And that will unearth what is the line, So let's talk about message delivery semantics. This is a cool diagram, right? When I showed it to my coworkers first, they said, oh, man, this is really cool. I have a question. And they said, is this? And then I said, no, there's no octopus involved, and the triangle really isn't angry at the square box. So we have a system here. There is this Akka system, and it boots up, and it wants to recover these messages. So what happens? I have the active system startup, and it contacts its store, some persistence thing, and it pulls up in number 1 the offset where it wants to subscribe. So I have this journal in Kafka, let's get the word out, that contains all the messages. It remembers the messages, right? They don't get lost. It's not a traditional message queue. You put stuff in and it stays there until, a couple of days later. And so I can say to Kafka, I want to go back to number 87, or whatever it is, 97 it is. And so that's the number I pull out from the database. And at point number 2, I'll go to Kafka and say, okay, I want to subscribe to a particular topic, but I want to start receiving messages from number 97. So I have a big queue of messages, right? And I'll go, I want to start from here. And Kafka is going to say, okay, cool, yeah. I'm going to send you a message. That's point number 3. So the service consumes a message, and it confirms it immediately, right? As soon as we have it, we're going to reply to Kafka and say, yeah, we have it. Now, that means that our service is actually fairly responsive. As far as Kafka is consumed, this is a really lively consumer. It gets a batch of messages, in this case just 1, right? It gets a batch of messages, and right away it says, I have it. Same thing happens in number 4, right? This is at stage 2. We get another message, we confirm it immediately. Now, if we crash now, you can immediately see what happens, right? We haven't gone all the way to number 7, where we write the offset 9a. So when the service starts again, it'll go, okay, I go to my database, what's the number that I have in there? 97. Okay. And it retries, it replays the messages. But if all goes well, right, we get to number 5, confirm, we move to our completed state, we produce a message, that's number 6, we get a confirmation from Kafka the message has actually been delivered. At that point, we write to our offset store the value 9a. Because now we have actually consumed the state. We had this transient state in numbers 3, 4, and 5, and then we produced in number 6, we got the confirmation, the value is in the offset store, so when we recover next, we'll start obviously from 9a. This should be, yes, everyone happy? I mean, you're just sitting there going, well, I don't like this. Shame, you have to do this. There's no other way of guaranteeing that you won't lose stuff. Now, of course, the danger in that is that you might do some duplicate work. You might receive duplicate messages. But that's the price we pay for having distributed systems. So, before we get into even more details, right, it gets slightly worse in failure. And when stuff starts going wrong, it begins to be even more complicated. But before we do, we have, in design of this system, we thought, how are these components going to talk to each other? What protocol are they going to use? And we just happened to settle on protobuf for a couple of reasons. First, it's actually, the syntax is nice. It's kind of cool to write these messages, really easy to use. Second, the tooling is actually really, really good. So you can generate the code in SBT, you can have the case classes generated, you can do even more interesting stuff. But for now, we have a message called ingested image, so that's the stuff we ingest. It's a media type, it's a string, and bytes content. Anyone, if you haven't seen protobuf, that makes sense, right? If you have seen protobuf, it makes sense even more. Nothing too difficult. But sometimes it's actually really helpful to wrap these messages inside an envelope. You might want to track some sort of correlation ID. You might want to track some headers, maybe. Before I go on, there's something that horrendously annoys me on this slide. Can you spot it? Mm-hmm. What's that? There is one at the top. So there's any, if that's your annoyance. Oh, bar. Bar is fine. I thought, bar, that's later today. No, okay, never mind. Anything else in terms of code? Semicolons are annoying. Okay, anything else? Come on. Any is annoying. Okay, I'll get to you. Any is bad. There's something else, like deeply offensive. What's that? String, okay. Come on. Where is 2? Exactly, where is 2? There is 1 and 3, and where is 2? Hang on to that. That will be the next slide. Any, I'm not forgetting you. So any isn't the Scala any old anything. This is slightly more restrictive. It's any protobuf message. So what we have is an envelope, and for sure this payload field is protobuf representable message. So it's not that horrific any, it's just slightly restrictive any. And hang on to number 2. That will become really, really important. For now, though, we get a message, we pack it inside an envelope, we generate correlation ID so we can track it, the message throughout the system, and off we go. We generate the case classes, right? So all that we do is write this protobuf file, and then when we say SBT package, it spits out, using this stuff, it spits out the case classes, it spits out the marshallers, all that you need. This is kind of neat. You can use this for your JSON marshallers, right? There's nothing forcing you to represent these protobuf messages as protobuf format. You can have them marshaled in JSON, and you can use it in Akka HTTP. What is really, really, really neat is that these protobuf files, these protocol definition files, end up in their own repository. And then what you have, if you have a large team working on multiple services, if there's a pull request to that repository, the entire team should go, what's that? Are you breaking something? You are inventing a new version of this protocol. That could be bad. And I don't have like a computer answer, but this is like a human process. You need to look at it and make sure it's forward compatible and backward compatible within a major version. The usual semantic versioning things. Now, you can do C++. Did I forget to? Did I not mention that? I mean, we're at Scala Days, right? But we were making microservices, and the promise was that you could use anything you want. So sure enough, you could do C++. The generated code, though, and whatever serialization tool you use, you need to look for a thing that generates code that fits, right? So this ingested image with underscore for content type, if you remember, right? We had this. media underscore type. You'd go, oh man, this is in Scala, right? But no, the generated code gets camel cased, so it's media uppercase type. It looks good, it fits the environment. So that's something you should look for in your choice of protocol. You might say, protobuf is, I don't like it. It's too slow, too big, I'm going to use Avro. Sure, make sure the tooling is right. Of course, we all do property-based testing. This is where you go, yes. Okay, yeah, okay, you said yes. But you could do this in C++. You could write property-based test. And so what do we, this is really trivial, right? So we're testing the mechanics of protobuf. What we're saying is, for any gen message, for any instance of that, if we serialize it and deserialize it, we get the same thing. So, well, okay, that's reasonable test. But of course, the values inside gen, the field MIME type and the field content, the values for it are generated by these property generators, very much like Scala check, except it's called rapid check. But hey ho, this is C++. Never mind that. There's one more thing before I move on. It's really, really tempting to look at, let's say, this scenario where we have this microservice in the middle and it takes an ingested image and it produces a thing that looks just like it, right? It might have done some fancy image manipulation. It has improved the image, right? You know, CSI, magic, zoom, and you know, it has done that. But don't ever recycle the same messages, right? It would be so tempting to have ingested image and ingested image on the other side. Now, if you do that, you have locked two microservices or more together. Now you share a message, you share a protocol, and that's a terrible place to be. Again, if you happen, I mean, looking at the lines of code, right, if you happen to be using protobuf, it's not really too onerous to write 4 lines of code, even though they have the same fields, right? Media type content, same stuff on the left, same stuff on the right, but give it a different thing. It's a different name, it's a different message. If you do it, you really decouple your microservices, and you will be able to change things independently. You will focus on one thing, changing one microservice at a time. All right. So I have other messages. Has anyone been hoffed? Okay, see, no. You're nice. This happens in our office. This is the next worst thing. You leave your computer unlocked and stuff happens. Now, this is the same for us. Okay, before we go on, has anyone looked at value-based authentication versus reference-based authentication and authorization? Excellent, no one. All right, no, maybe I'm just using big words. I'm a simple man, so I should stick to £5 notes. Okay, imagine that you want to present payment. Think that the payment is authorization for a service call. And if I bring genuine £5 Scottish note, you would be able to take a look at it. It's a value. Right? You can look at it, verify that it has the right security features, and you would be able to authorize that call without reference to anything else. Right there you can decide. Versus this GUID, right? So this could be like a session ID or something. If I give you a session ID, think a credit card number, and say, I want to pay for this service call. Here's my GUID that links to my bank account. You have to now make a call to the bank. Without that call, you cannot decide. And so in microservices, right, it's always better to use value-based semantics, where this thing, the authorization that you present with every call, contains everything that the service needs to do to decide whether to allow the call or to deny it. Okay, before I go on, any Doctor Who fans? All right, can you see it? Okay, I'll give you a hint. Oh, ho, 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 right? We're such geeks. It's fantastic. So, obviously, we don't present £5 notes in our code. We use a thing called JWT. So we issue these tokens. JWT, think JSON, right? It's just a structured JSON with either a digital signature or it is encrypted. And so we will add in 2 more services, authentication and authorization with their databases. So we have table users. Okay, fantastic, and table permissions. Brilliant. So next question I have is this. And this is really, really strange. You'll be really annoyed. What if these two databases are gone? What if they're not available? We should be, resilient. So I'm logging in, but that MySQL that contains table users is gone. What would you do? A similar story for the authentication, right? So I've authenticated, and I want to get some sort of token, and I say, here's a thing I got from the authentication service. Now give me a thing that I can present to all these other microservices that prove that I am who I say I am, that I can make the call. And this is a tough one. This is surprisingly difficult. One of the choices is allow everyone. And it's a business, okay, where I'm heading is this is a business choice, right? The lines of code that actually implement whatever logic someone decides, they're the same. But what we're able to say with reactive systems is, look, there is a very, very strong possibility that this user database at some point will be unavailable. What would you like to do at that point? And the options are, deny everyone. So someone tries to log in, something has broken in your system, and you say, this is a 503. No tokens are going to be issued. And the business might say, well, this is terrible. I want people to gamble, because that's what it ultimately is. They're placing their bets, and for that they need to take a picture of their ID, and I need to allow it. So what do we do next? So the next option is, well, why don't we issue this very, very short-lived token, regardless of the username and password? Anything goes. And we're going to give back a token that says, yeah, that's allowed. But the token is valid for 3 minutes, 2 minutes, I don't know. Pick a number. Randomize the value as well. So you say 10 minutes or 2 minutes with a random factor of something, so that when the client, the timeout expires, the clients will have to go back to your service and say, give me a new token. The one I have is no longer valid. Or hopefully by then, your user database will have become available again, and you can really do the check that you need to do. So this is a wild story, right? Why would you allow anyone in the system? But it's a decision you'll have to make. And the cool thing is that with all the technical tools that we have under our fingers, we can force the business to make that decision. And they will give us a decision, and we can implement it. The lines of code that make up the implementation, simple. Whatever the decision is, but force the decision. Okay. So number 2 was that token. We package it inside every envelope. Because the next thing that you really shouldn't do is to have one microservice right at the start, your gatekeeper, your REST API, and it will check the tokens, and then anything that gets in, it's fine. Anything goes, right? Once the message is inside your system, any service can handle it. That's a terrible idea. Every service should check the claim. So, we, in this system, happen to have encrypted the token, which brings all sorts of problems with it, namely key management. It's your decision, right? If you don't encrypt the token, you give someone essentially the £5 note, and they are looking at it and going, oh yeah, this is £5. I can see that you're using £5 to get something. If you encrypt it, you get this envelope, brown envelope, and inside there's something, you don't know what it is. But of course, you need to have something that can unseal it. So you need to bake in the keys. Now, you really need to think about good key management. It's a terrible idea to take the key and bake it inside your Docker container that you deploy. That's really not a good idea. So depending on where you're hosting the service, think about where the keys go. But then you check it, right? Point number 1, you get the private key in this case, and in point number 2, you extract it. You wire it into, say, an actor here that receives a batch of records from Kafka. The records from Kafka, remember we said every service should check the claims of the message that it's receiving. So we really should check. So let's first make sure that we get the token. Let's make sure that there is a claim for the microservice push ***. You can even use that for versioning. And the value of that claim can mean something. So what you're able to do here is someone logs in, and you can issue a token that says, for you, right in the audience, I'm going to give you a push token that actually goes to your beta version of your backend system. Everyone else here gets the original value. So the claims aren't Booleans, yes or no. They have meaning that you define in your system. That's line number 2. So you want to be reactive. That's, that was the name of the talk. That's why we're here. So let's first be responsive. So, okay, how does that work? In this case, this is a complicated stateful service. So what on earth is going on? Line number 1, we have subscribed to Kafka, right? And it has sent us this batch of messages. So we have, let's say, 5 messages. Now, this actor builds summaries based on transaction ID. That's how we work. And so line number 1 is plain old Scala code, right? We have some summaries, which is our own data structure, and we append the consumer records, and what we get out of it is new summaries, the outcomes, the things where we have the 3 messages, if you remember the slide earlier, and then offsets. Now, what on earth is that? Well, first of all, new summaries, that's easy. That's simply the mutated version of summaries. Okay, we're happy. Now, outcomes and offsets. Remember, we only want to write the value of our offset storage when we have read all the 3 messages, when we have successfully produced the value. So offsets are essentially the smallest values of the offsets that we can safely write, so that when we crash, we can recover precisely to the state that we were at point number 1. That sounds really complicated, but it's not that hard. The only thing that makes it complicated is the fact that there are multiple transactions happening at the same time, multiple records, right? So batch of records from Kafka, they might be relating to multiple users. We don't know. What we want to know is to look at the stuff that we have inside our actor, produce the outcomes, so that's the value of outcomes. When we send the outcomes, that's line number 3, right? We will then take all the values that we want to send, all the messages that we want to produce. When it works, so that's line 3, persist offsets, we have produced them, we have received confirmation from the topic that we have put the messages to that, yay, they are delivered. At that point, we write stuff to our own offset storage. If it didn't work, it's self-kill, right? So we want to trigger our supervision strategy. Now, you might have a question, well, surely we are inside receive. Couldn't we just throw an exception? Couldn't we? Come on. So no, right? And no, because we're in some other future. Now, this is very strange. If we throw an exception there, I can't jump that far. In the case failure, it wouldn't be throw inside receive, so we need to self-kill. But then what we probably want is a priority queue on this actor, so it prioritizes these kill and terminate messages. So there's a useful tip. Now, we want to be resilient. So I was saying, okay, what if this user database is gone? And we said, yeah, no, okay, if the user database is gone, we will allow anyone in. Okay, that's reasonable. What if this offset storage database is gone? What do we do? So imagine the scenario. This service is running, right? So we're here, we're running. Everything is cool. We're receiving messages from Kafka, we're producing the messages, we're mutating the summaries. The only thing that doesn't work is persist offsets on line 3. And it doesn't work because the whatever thing, like Zookeeper, where we write these offsets, somehow we cannot reach it. From our point of view, it's unreachable. So what can we do? And this is a neat balancing act, right? What you could say is, never mind. Like the first reaction is, never mind, we'll just carry on. After all, we are running. This service is running. It has its state in memory. That's all cool. The only thing it doesn't do, it's not able to write the offsets into Zookeeper. Now, if we allow that to happen, suppose we did, the price we're going to pay in case we crash as well is the fact that we're going to have to replay more messages, because we haven't written the offsets. So like the last value is 97. We have now processed messages all the way to, like here, 200. And we crash. And then we go back to this Zookeeper database and say, what's the last value that you have? And it's going to say 97. Oh, wait, it's crashed. It's not going to say 97, is it? It's gone. Well, what do we do? OK, let's look at the code. What do we do in line 3, right? So let's focus on 3 and 4. So in line 3, and this is an example, you might not want to do this, or you might, depending on, I'll give you the reasoning for it. So read from Zookeeper returns offset, so it's a map of topic name, partition name to this number, right? How far we go into this offset. Now, suppose we crashed because Zookeeper was unavailable. Now the RJVM comes back up, and it tries to read the offsets from Zookeeper. Of course, that fails because Zookeeper isn't still available. Well, the option that we have in line 3 is to simply say, let's go back all the way to the beginning of time. So it doesn't matter how many messages you have, we're going to start right from the beginning. That's possibly not a good idea, because you would have to replay every message from the beginning of time. So you don't want to do that. So what could you do instead? You could say, well, let's just begin at the very last end. Right, so we're here. The problem is we've missed all those messages. We simply don't know about them. So we have failed our message delivery guarantees. Another strategy is, we're here, this is the end of all the messages. What you could say is, we're going to go, 200 messages into the past. It's a magic constant. Because you know how your system works, and you're going to say, I'm going to subscribe, but I don't know where I ended up because my dependency is gone. So I'll just take a gamble. And this magical constant, I can't tell you what it should be. You know because you've written your system. But remember, you are only in this scenario because something has really gone horribly wrong. You've crashed because you couldn't write, and now you're recovering, and the thing you couldn't write to is still not there, but you need the value. You really need it, like the user database. So that's what we can do in line number 3. Whether you return 0, that last value, or some last value minus 500, or some other constant, doesn't matter, right? That's just one line of code. This is nice and simple. Okay, now line number 4 is where we write the offsets, but we want to write with a circuit breaker, because we want to be notified when this Zookeeper operation fails. So what do? Well, we define a circuit breaker on line number 1. We specify the max number of failures, the timeout for the operations that happen inside the future that's returned in number 4. And when the circuit breaker opens, we kill our actor. We kill this guy. Because we have a supervision strategy that says, oh, okay, here is how we deal with failures, and kill is the thing that triggers supervision strategy. So like these few lines of code actually give you a fairly robust way of detecting and recovering from failures. And even if stuff goes horribly wrong, your system can survive. And you have these tunable magic constants, like the timeouts and the number of retries. And you have this magical constant 0L at point number 3 that you can use to really tune how your system is going to deal with terrible crashes. But it will survive. Okay, fine. One last thing. We're nearly done. I know coffees and other exciting talks, but promise you, last 5 minutes. Okay, so same thing. We said check claims in every service. Tick, 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 tick. We do that. We decode all of this. Now, in just below line number 1, we said, okay, we have this fantastic protocol definition, so that describes the sort of syntax tree of the stuff that's inside our messages. We could use it to construct JSONs, right? There's no reason to say to all of our clients, guys, you have to use protobuf, like the binary stuff, because it's cool. No, we do JSON. So that's, we do JSON format to JSON string from the arbitrary any, but don't worry, Google protobuf any, not any old any. And we produce a message, the stuff that we're going to send to our clients, right? Except we want to be nice to our clients. If they start failing because they can't keep up with the message rates that we produce, we want to be able to back off nicely. But we still want to keep the messages in some store until the clients can pick it up. And so we're going to do CQRS. We have this write side. So we've checked the claims, produced everything, persist all, that's standard Akka persistence. On completion, so when persist all of this collection of messages out, the stuff we're going to send to our clients, when it finishes, we're going to confirm to Kafka that we've received the batch of messages. So we're still resilient, we're still responsive, and we remain resilient because we don't lose the messages. Now, we want to probably group the push view because the push actors' views, really, we should have an instance per client, right? You don't want to mangle messages for different URLs. So you might want to do something like that. Remember in the previous slide, we've used persist all to write a batch of messages into a journal of some kind defined in your Akka configuration. Well, you can then, as you start up these nodes that make up your system, you can make instances of this push view because you know what your clients are. You have the URLs. So you can make like 10 instances of this guy, each with a different URI tag that defines essentially where to put the stuff to and where to begin reading from the offset. And then you take the Akka HTTP superpool. Say, oh, you know what? We're going to be making HTTP request. You actually spend the time implementing these functions. Don't worry, you can clone them on GitHub. It's all there. It's just code. And then, nice, Akka flow. Line number 3. What we're going to do is take the source, which is a source of aggregate events aggregated by that tag URI. So we've written, there was one actor that wrote all this stuff to the journal. And now we're getting views that essentially read different slices of this journal. We're going to send all these events that we pulled out from the journal via this HTTP pool, so that actually makes the requests in this very, very fancy asynchronous back pressure aware way. What we're going to do, that's the grouped within 10 or 60 seconds, we're going to say, okay, you know what, we're going to group 10 requests at the same time, or we're going to wait for 60 seconds and we're going to send those batches to our clients. For every request that we send, we're going to commit to our own offset how far we got, right? So that when we create a new version of this view, we don't resend the same request to the client. And suppose we don't really care about the responses that we receive, so we'll run it with sync ignore. And we're smiling. We have back pressure aware, stuff that reads from our journal, that we can group, that we can control, and it's not that much code in the end. So again, now, okay, all of you people, you're looking at this going, that's nice, that's nice. Persist all, yeah, that's kind of nice. What's the format of the stuff that ends up in the journal? Because if you do Java I/O serialization, you'll be in deep trouble. You change that, you change one little tiny thing, and you can't read the messages. What about the payloads, right? You put payloads into this journal, and then you change the protocol. What do we do? Well, we are going to cheat a little bit. Because what we're going to persist into this journal are the HTTP entities. We're going to define a protocol for them, but what it means is when we change the protocol for the payloads, that doesn't matter because the entities are persisted. The entities have the payload, the bytes that make up the request. So we don't actually have to do anything too clever here. What we just do is pull out the bytes from the journal and say, those are the bytes that are going to the client. I don't care what they are. That was someone else's job. So it's a neat way of, it's not cheating, it's just think about the least amount of work that you'll need to do, particularly when you save messages, particularly if you want to be compatible for future versions of your services. Alrighty. So we have the holy grail, right? We can assemble magical, reliable, safe systems. So we don't want to do that, but this is history, right? I mean, come on, 600 megabyte hard drive. Yeah, this goes back. So if you do this, if you follow the principles of the Reactive Manifesto, particularly around being message-driven, resilient, responsive. Elastic, suppose we know how to do that. That's easy. Elastic is given. But responsive, resilient, message-driven. You are able to, first of all, write the code in whatever language you like. So we used a lot of Scala and Akka here, and that's great. So we can have our persistent, our summaries actor, which uses Kafka as its journal. You can then have ingestion route with Akka HTTP. You have these push actors, which are persistent actors, push views, yada, yada. All that goodness is for you. You could do this. Now, we had to do that because we inherited some sort of CUDA-based library, and now that's how grim it is, right? And this is nice, modern, I like to think, C++. So, we get fancy stuff like unique pointers and But it's pretty bad, right? No one wants to write this stuff. But you can, the idea, okay, fine, no one wants to write it, but then again, we are getting paid to write some code, so there might be time where you have to. But the cool thing is, all the tooling that you've selected fits, right? We are still able to receive messages from Kafka in an asynchronous way. We are still able to produce these extracted phase and ingested image. They are the case classes, or they are the protocol messages that we defined in our protobuf. We are able still to do property-based testing in C++. It all fits, right? This is the holy grail of microservices. People said, okay, come on, use any language you want. And we all said, yeah, I know, but we're going to do Java, aren't we? No, we really can pick the right thing. We're going to do Scala, because we like it. We're going to do some C++, because we must. We might have people who do Go, because they are super cool. But it all fits together. Doesn't matter what this does. So, okay, there you go. I promised you on-time finish, and we're on time. So now it's your turn. If you haven't yet, stop by at our stand, pick up the preview of the book. That's the sort of, what color is that? I don't know, weird blue fuchsia color. So pick up those. We're about 4 chapters in, so the whole thing will be released, we're thinking November. And then, of course, write the code, clone this, and run it yourself. You'll get the C++ code base, you'll get the ingestion microservice, the push microservice, the summary microservice. You can build all these containers. You can then run a whole bunch of other Docker containers, and it'll be a success, right? You'll get all this. Okay, don't worry, I'll tweet the links and everything. So stop by for questions here, but I'll do a bit of a summary. It's really, really important, these long-lived systems. The main thing we found, like a critical light bulb moment, was the idea of being message-driven. The idea that a service will produce messages, but it doesn't know who's listening. It doesn't have to know specifically who's listening. Because if you do that, then it allows you to build a system that can accept new services that you haven't discovered yet. It fits, though, systems where you know about the services. Because we are really, really message-driven. It is not one message comes in, exactly one message comes out. You sort of forget that. You say, you know what? I'll publish a message, and then I will receive from some other sources maybe multiple messages back. And you can use, you can build state in each of your services. You can then really, really, really isolate the services. If you publish, there is no reason why you shouldn't have multiple subscribers. I'm sure many other people will put it in a much more eloquent way, but in a distributed system, you will end up with a lot of data duplication. There are things you will have in multiple places, and you actually want to do that because you want to survive failures, and because you want to isolate all your services really, really sharply. Don't share a database, that's pretty obvious. Don't share message formats. Don't share anything if you can get away with it. And now, of course, there are technical details of, you might have some common validators, common stuff, but that's a different deal. So let's finish on that note, and I'll thank you for your attention, and come and speak to me here or at our stand with any questions. Thank you very much.